Hello and welcome back to this course. So, we were discussing about the efficiency calculations wherein we saw the total efficiency is a product of three sub-efficiencies, that is thermodynamic efficiency, voltage efficiency and the fuel efficiency. So, in case of fuel cell, we need to find out all these three efficiencies, and once we multiply them together we get the total efficiency. I can also simplify this a bit. So, total efficiency is nothing but, as we know in case of thermodynamic efficiency, it is E naught by ETH. Voltage efficiency is your operating potential by reversible cell potential, and fuel efficiency is 1 over utilization factor. So, this naught gets cancelled and what we have is operating potential divided by thermoneutral potential times the fuel utilization factor. So, once we know the operating potential, we already know the thermoneutral potential, and if you know this fuel utilization factor as well, or in other words what is the excess amount of fuel that is supplied to the fuel cell in percentage, we can find out the lambda, and once we know that we can find out the total efficiency. Let us go ahead and solve very quick examples. So, let us take a simple example wherein we have a stack of 10 cells with the active area of each cell is around 300 centimeter square. Fuel utilization factor for hydrogen is around 1.3, and for oxygen is also given as 2, and performance curve is also been given. So, we need to find out the flow rate of hydrogen, actual flow rate of hydrogen that is required at 3 different efficiency operating points. This is my operating point number 1, this is 2 and this is 3. So, this is operating voltage is around 0.8 volt, open circuit potential is let us say 1 volt, this is 0.6 volt, and this is 1.3 volt. We have current also been given at these 3 points. This is somewhere around 200, this is 500 and this is 800. They are all current densities. So, let me write that current densities. So, that is a new term in milliamps per centimeter square. So, we will have a look at what this current density means after this numerical. So, we need to find out the flow rate required at these 3 points as well as the total efficiencies at these 3 points. So, let us first write our equation of the fuel cell, which is at 1 mole of hydrogen combining with half mole of oxygen giving 1 mole of water. So, this is our conversion reaction. Let us take the first point. So, first operating point So, what is my first operating point? What is, let us first find out the total current that is flowing in the stack. So, how do you find? So, current, or let me write total current is 200, this is milliamps per centimeter square. So, we need to find out in current in amperes. So, we need to also multiply with this area of the one cell, which is 300 centimeter square, and since this the entire amount will be in milliamperes, this will be 6 4 zeros 60,000 milliamperes. So, that will go around 60 amperes of current. So, here we need to understand that all these cells, the 10 cells are connected in series combination. So, the current that is flowing in cell 1 or cell 10th or even cells in between will be same throughout. What gets added up is the potential of all these cells. So, I found out the total current flowing in the stack. Let us go ahead and find out the minimum flow rate required. So, m dot h2 theoretical, or I can write like this, which is I n v by nf. So, we know the total current flowing is 60 amperes. There are 10 cells in a stack. Molar volume is 22.4 liters. N is 2 for hydrogen. Faradays is 96,485. So, if we solve this up, let me go to the next slide. So, m dot hydrogen theoretical is basically, so it comes somewhere close to 0.06964 liters per second. I can convert this. So, this is a slightly odd figure as it is not very comfortable to measure. So, we need to convert this into liters per minute or liters per hour depending upon the flow rate. So, that comes close to 4.178 liters per minute. So, I have just multiplied by 60 so that it gets liters per minute. So, this is with respect to the first point, or I can even convert this into the mass flow rate. So, flow rate of oxygen theoretical is basically half of this, as we have discussed, hydrogen theoretical by 2. So, this is 4.178 by 2, which is roughly 2.089 liters per minute. So, this is for the case of first point. Then let us go ahead and do it for the efficiency calculations. For the first, total efficiency is basically thermodynamic efficiency into the voltage efficiency into the fuel efficiency, or I can even write it as, I can now substitute. So, thermodynamic efficiency is 83%. So, this is 0.83 times voltage efficiency. I can, for the first point, it is 0.8 is your operating potential divided by 1.23, and fuel efficiency, as we know, it is for the hydrogen, the fuel utilization factor is around 1.3. So, this is given. So, let us go ahead and find out for the first case. So, it comes somewhere around close to 0.4153, which is around 41.53%. So, this is my total efficiency for the first operating point. So, we need to do the same for the rest 2 points. So, let us see and find out how we can do it. So, for point 2 and 3. So, let us first find out m dot h2 theoretical, it is I n v by nf. So, my current, total current flowing in the system. So, total current, let me write it here, total current is current density, which is around 500 milliamps per centimeter square. So, this is milliamps per centimeter square multiplied by the area of one cell, this is in centimeter square, divided by 1000, that will be in amperes. So, if I do that, this will be around by 3. So, roughly 150 amperes. So, let us put that total current as a value as 150 amperes. There are 10 cells in the stack and molar volume is 22.4. we are talking about the hydrogen flow rate. So, N should be 2, Faraday's constant same 96,485. So, if we calculate this, this comes somewhere around 10.447 liters per minute, and we can also find out m dot O2. This will also be theoretical. So, this is half of the theoretical flow rate of hydrogen. So, it is 10.447 by 2, comes close to 5.2236 liters per minute. So, let us go ahead and find it for the third point. So, for third point we have operating potential as, sorry, I forgot to find out the efficiency. So, efficiency for the second point is again thermodynamic efficiency into the voltage efficiency into the fuel efficiency. So, let us substitute all the terms. This is 1.23 by 1.48. Voltage in the, for the second operating point is 0.6 volt. So, we are talking about this one, this operating point. So, potential is 0.6 volt divided by 1.23, and fuel is again given as 1.3, that is your fuel utilization factor for hydrogen. So, if we calculate this, this comes close to 0.3118, or this can also be as 31.18%. This is total efficiency. Let us go ahead and find out the for third point. So, let me write 0.3. So, 0.3 is first point m dot H2 theoretical, it is I N V by Nf. So, current flowing is, current density is around 800 milliamps per centimeter square into current, the area of the cell is 300 centimeter square, and it has to be in amperes into 10 to the power minus 3. N is again 10 cells, molar volume is 22.4 liters, N is 2 and F is 96,485. So, that gives close to 0.2785 liters per second. So, this comes close to 16.715 liters per minute. So, that way we can also find out for the efficiency for the third point. So, that is eta total, it is 1.23 by 1.48, operating potential is 0.3 volt by 1.23, and lambda is 1.3. So, this will give us the total efficiency in percentage. So, that way we can find out for every operating point, and if we see that as your voltage is dropping, as we go and extract more and more current from the cell, as we can see here, the voltage drops continuously and subsequently the efficiency also drops. So, that means where we have to be very careful where we have to operate our fuel cell, such that we take the best from the cell without compromising much on the efficiency loss. Next point is basically the importance of current density. So, that is denoted by capital J in IV curve. So, we just had solved a numerical and we have seen that the IV curve is typically shown, instead of showing like a current, it is showing, it has been shown the x axis is shown in terms of current density. So, current density. Now, this is a very important parameter that we need to understand in terms of the while we present the characteristic curve. Let us suppose for this moment we assume that we are showing IV curve in terms of only current, not the current density. How it will look like for the different cells. So, let us say I have a one cell which is of let us say 5 centimeter square. I have another cell which is slightly bigger of let us say 25 centimeter square, and then we have another cell which is even bigger of let us say 100 centimeter square, and so on and so forth. I want to compare these three cells based on their performances. However, we have to understand that larger is the area of the electrode. This is the area of the electrode. All these are the areas of the electrodes. So, as the area of the electrodes increases, the current output also increases, provided all the the materials and the I mean they are all assumed to be performing on a satisfactory scale. So, in other words, so if 5 centimeter square cell is let us say we have, it will probably we will be able to fetch roughly around 5 amperes of current. So, it may have its current density curve something like this. This is my 5 centimeter square cell. I can draw for the 25 centimeter square, it will be like this, and for 100 centimeter square, this is for 25 centimeter square, and for 100 centimeter square it will be even bigger. This is for 100 centimeter square. This is for 5 centimeter square. So, if we have a closer look at this profiles or the characteristic curve, the first impression or the obvious impression that we get is a cell with 100 centimeter square area is performing better because it is producing larger amount of current compared to the other two. That is not the case. We have to normalize their performances based on some parameters, so that once we normalize their performances, then and then only we will be able to compare and evaluate the performances of different cells of different areas or different compositions. This is very similar to the sports, like we often see, for example, wrestling. So, in wrestling, we have different weight categories. So, we have a person having let us say 45 kg. We do not see a person weighing 45 kg to wrestle with a person having 90 kg category. So, this why there are been different weight categories, because then and then only we can have a fair competition between the two, and we can also see that if we allow a person with 45 kg to fight with 90 kg person, he is obviously going to lose the game, or on a basic approximation it is going to lose the game. So, in order to normalize their performances, who did the best, so they have been categorized with respect to weight categories. Similarly, in order to have the fair comparison between fuel cells of different sizes, or we can also compare them on different materials, they have been normalized with respect to area of the cell. So, that current density is nothing but the total current flowing in one cell, flowing in a cell divided by the area of the cell. So, that is what the current density means, and it is denoted by capital letters A. And if we now try to plot the characteristic curves of these cells, you will find that we will be very surprised to see that let me use the same colors. The cell having higher area performs inferior. So, this is for 100 centimeter square cell, and for this is for roughly, this is 25 centimeter square cell, and for 5 centimeter square cell performs the best among the class. So, this is 5 centimeter square cell. If all the cells are having similar compositions, then even things are, we can compare it even in better fashion. So, why is this happening? Because as the area of the electrodes, as I have already mentioned, as the area of the electrodes increases, there are more pathways for the, or rather there are more chances or more sites for the reactions to occur. So, for example, if I have 5 centimeter square cell, this is 5 centimeter square cell. So, number of the reaction sites are limited in number. However, if I increase the area of the cell, then we have more reaction sites on the electrode, and that ultimately leads to more rate of those reactions. So, as the area increases, that implies the sites for the reaction increases, and that ultimately leads to more rate of reactions. And as we understand, more is the rate of reaction, more will be the electrons per unit time in the circuit, and that ultimately leads to higher current. And that is one of the reasons why larger area cells have more current output compared to smaller cells. But that is very unfair to compare only based on the current, and to have a very fair comparison, the performances curves are typically presented with respect to current density. So, that is how we can compare the different cells, and then we can have a very fair understanding about the performances as well as the evaluation of these cells. So, moving on, once we have understood the significance of current density, let us also understand how the power density works. So, or let me write significance of power density, of course with respect to current density. So, let me take the same examples again. So, this is my current density in, let us say, in milliamps per centimeter square, and let me take 3 operating points. This is 0.8, then we have 0.6, and then we have another same point, and let us say 0.3. So, current density is here 200, here I have taken 600, and here I have taken, let us say, 1200. So, how does my power curve looks like? So, we all know what is power. Power is basically product of voltage and the current. So, and this power density is nothing but voltage into current density. And for the first case, let me write power density is basically we have voltage as 0.8 volt and current density is around 200. So, this will have a power density of 160. This will be in milliwatt per centimeter square. Similarly, for power density at second point will be 0.6 times 600. So, that will be around 360 milliwatt per centimeter square, and at third point it will be power density will be at third point will be 0.3 times 1200 will be around 360 milliwatt per centimeter square. Let me take another point at let us say 0.1 I am considering, and here I am taking current density as 1400. So, my fourth point will be 0.1 times 1400. So, that is my 140. Milliwatt per centimeter square. So, if I now try to plot these numbers 160, 360 and 140 at respective points. So, let me use the another vertical. This is power density axis or vertical. This will be in milliwatt per centimeter square. So, as we can understand, so first point is at 160. So, when we have a zero current flowing in the circuit, we have zero power density. So, our first point of the power will be here itself. This is 0. Then 160 will be somewhere around, let us say here, the same vertical. So, let us say it is here. Then 360 is here. Then I have, in this case I have taken the power is coming same in second and third point. So, there will be a plateau here. So, or if I neglect that point and if I go ahead with the fourth point itself, which is again at 140. So, it will be somewhere around here. So, it will go, the power density curve will go something like this, meaning that there is one operating point somewhere here which will have maximum power density. Or it is called as P max. So, and this P max, as we understand, it is the point where your ohmic zone is about to get over and we are entering in the mass transfer zones. So, if we draw this very correctly, this comes close, this comes something like this. So, this is my IV curve and the current density curve looks like this. So, this is our P max point and this is very close to end of your ohmic zone. This is our ohmic zone and this is our mass transfer zone. So, this what it implies is we always get, or by and large we get maximum power density point or maximum power output point somewhere at the end of ohmic zone and beginning of the mass transfer zone. However, in real practice, this is not the point where fuel cells are operated. Fuel cells are typically operated close to P max, but however in the ohmic zone somewhere, so that we have some play here and any fluctuations in the current density can be absorbed, so that we do not end up in the mass transfer zone. And as we understand, mass transfer zone is highly hostile. It will end up in catastrophic failure of the fuel cell, as there is a sudden drop in the potential. Hence, the mass transfer zones are very dangerous and they are typically avoided in fuel cell operations. So, with that, I thank you all and we look forward to more interactions on this course in the upcoming sessions. Thank you all.